And I will end with one last thing, which is called population inversion. Population inversion. What is population inversion? So normally, we know this, in thermal equilibrium, atoms absorb and emit at the same time. But if N1 is greater than N2, that means the number of atoms in energy 1, the lower energy, is greater than number of elements in N2, what will happen? Absorption will be more, right? More of the incident photons will be absorbed rather than cause emission, because they will excite the atoms first, right? However, if we can find a particular material, that could be induced, that's a nice way of saying forced, to have majority of its atom in the excited state, that is when N2 is greater than N1, then we will have something called population inversion. What will the elements want to do when most of them are in N2? They will want to go down to the ground state, yes? And in that case, what will happen? Remember, we were putting more photons in, so 2 will be emitted. They're already in the excited state. With very little simulation, more will be emitted. So on their way to the ground state, the system will likely laze. So note this word carefully. And what would it look like? A normal material would look like this, more than likely. So it will have more of its elements in the ground state, fewer in the first excited state, and even fewer in the next excited state. This is what normally will happen, right? Most of the atoms will be in the ground state, few will be in the excited, and even fewer will be. So imagine if you have this condition. In population inversion, the condition would be something like this. And I will stop here. So E1, E2, E3. So that's population inversion. So I have not yet talked about lasers, but I have taught you that they are materials that are likely to laze. I've almost given you LASE. What do I have to add up? We just have to add an R to this word. And then we will have laser.